All right, we're going to get started again with an update from OpenVDB. So I'm going to turn it over to Ken now.
All right. So yeah, we'll be covering OpenVDB and talking about sort of past and future. And this does not seem to be working. There we go. So it is a schedule. It's 3 parts. I'll talk a little bit about past, future. Jeff will talk about OpenVDB in Houdini. And then we have a guest presenter who is talking about adding Mathematica bindings to the project, which is quite exciting. But first I wanted to actually note that OpenVDB as a project has a 10-year anniversary. So last week, it was 10 years ago since we, this is not really working. Since we did the first release, I think it was August 3rd, 2012. And I'm stuck. Oh, there we go. So I don't want to be too sentimental about this, but I do want to give a shout out to 2 other co-developers that really helped make that first release possible, namely Peter Kuka and Mihai Alden. So now I'm going to cover a few highlights of the next version we're releasing in late October called version 10. It's not a complete list, I should highlight. So the first thing is there's a new type of grid in NeuroVDB called index grid. It's interesting because it allows you to use the grid with arbitrary types and even different channels. So this actually opens the door to modifying things on the GPU, values in this case. So you could have multiple read and write buffers. You can have arbitrary types. There's even a mode in which this grid type is more compact than the current one because it can actually eliminate inactive values. Then there is convex clipping, which is what Jeff will be talking about. So I won't steal his thunder. And then we have the Mathematica binding, which is what Greg will be covering. And then there is a tool. It's a command line tool. It's meant as a sort of a mini DCC. And I will actually go give a few examples of why this is a useful tool. And then obviously, a lot of other changes and modifications are also part of this release. And then after version 10, it gets a little fuzzy, but I will talk a little bit about an announcement that NVIDIA actually made today that we hope will eventually make its way into OpenVDB. It's still unclear, but it's a project called NeuralVDB, and it is being open sourced. Whether it ends up in OpenVDB or not, we'll see. And then we're also hoping for a very interesting contribution from the Bifrost team at Autodesk, namely a multi-grid structure. All right, so I'll talk a little bit about this command line tool. So the idea is, or rather the fact is that today most of the high-level functionality in OpenVDB is actually only exposed in Houdini. Which is awesome. Houdini is a fantastic tool, but sometimes you have very simple things that you want to do, and you may not want to, crank up a mega application like Houdini. You just want to type something and basically do it on the command line. So what this tool does, it exposes pretty much all of the high-level functionality as command options. And so I have a collection of very simple examples here. So this basically just shows us how you read a mesh file. You'll turn the mesh into a level set. You specify the voxel resolution, in this case, 512 voxels, and then you write it out again. So it's very simple stuff. This is another example where I'm actually reading in both volume, a VDB volume, and a mesh. And then I'm converting the mesh into a volume, but I'm using the voxel resolution from the other volume. And I'm actually multiplying it by 2. So I want twice the resolution in this case, or twice as large voxels in this case. This is an example where, again, we're reading points from a file, and then we have a string of operations. So first we're converting the points into level sets, then we're dilating them, and then we're applying a Gaussian convolution kernel, and then we're eroding them, and then we're streaming it to a pipe. So now we're combining it with another command line tool that's already in the library, namely the viewer. And this will allow you to, in a single command line, execute all of these operations and see the result in an interactive viewer, which is very, very useful. This is another example. It's a little more convoluted, but it shows you how you can combine shell scripts with this command line tool. So here I am using the Linux find command to find all the VDB files in a file structure. And then I am opening each of these files. I'm opening every grid inside the file. And then I have an if statement saying, if that grid is a level set, then render it and write it out to a file. So this just creates thumbnail images. And this is an actual example of how we use this tool in production. So at NVIDIA, we have written a fluid solver, and this is actually showing how we mesh the points using. So in this case, we're processing lots of different files, a whole cache of files that came out, and we're doing it with these. And in this case, you're also seeing how you can actually go in and make sort of fine tuning. Here, we're actually defining the spatial discretization as Reno, which is 5th order, the temporal discretization as 1, so it's 1st order, and so on. So there's a lot of different things that you can control. I should also point out that it has a file format, so in case you don't want to deal with these very long strings, you can take all of this and put it in a file and sort of edit it and modify it. So the other thing that we hope to welcome into the open source project at some point is this thing called NeuralVDB that was announced earlier this morning. It's a project at NVIDIA with 2 collaborators, Doyup Kim and Minjia Lee. And the idea is to use neural representations as a way to achieve very memory compact and file compact, footprint compact representations of sparse volumes. And when you think about it, a VDB data structure essentially has 2 types of information. It has topology information, which is essentially where are things placed in index space. And then, of course, it has values. And you can actually use 2 different types of neural networks to represent that very compactly. So you can use classifiers for the topology, and you can use regressors for the values. And the trick, of course, is that the classifier has to be 100% correct, right? Because if you get the topology wrong, you may actually lose a whole branch of your tree, which can amount to a lot of data. So this is a lossless classifier, but a lossy regressor. But you can control the level of accuracy. So you're seeing an example of the Disney Cloud. The Disney Cloud is, if it's just a vanilla VDB, it's almost 4 gigabytes. And if you're using the NeuralVDB, we can compress it down to 25 megabytes. And I just want to play this video. This is showing an A/B comparison between these are obviously level sets. So sparse sign distance fields represented respectively with an OpenVDB and a NeuralVDB. The OpenVDB actually uses half precision. So it's not 32-bit float, it's 16-bit float. And it also uses BLOS compression. So we've done everything that we could to make it as small as possible. On the right-hand side, you see the NeuralVDB representation and the compression factors. So it's typically between 10 and 100x. So it's quite aggressive. In this case, it's 60x. If you're interested, so we will open source the code, but if you're interested, there's also a white paper that is going live tonight at 5, I think. So another cool thing is that we can actually use, it's very good at dealing with temporal data, and we can actually use a simple but very useful trick to introduce temporal coherency in these animation sequences. So we can actually warm start a frame with the neural weights from the previous frame. And that actually gives us temporal coherency and also a little bit of motion blur. And it even accelerates the training session itself. So, yeah, that's it for me. And Jeff will now talk about.
Hello, my name is Jeff. I'm also a member of the TSC, but also work at SideFX on Houdini, where we've been working with OpenVDB, I guess, since before it was open. But and recently I ran into an interesting case, and so I thought I'd just cover how I used the dynamic node manager to solve a problem we ran into. So in Houdini 19.5, we did some more work with our flip simulator. We moved it into our SOP framework, but this also opened up the ability to really sculpt where the simulator was active and really control the domain of where your solve runs. Because if you have this character going through the water, you don't want to simulate the entire ocean of water, only the area roughly around where the camera sees. So, you know, a larger area such as this. So another way to look at it, if I had like the cylinder, I want to only simulate water inside the cylinder, you could see you want this little plug along the bottom, and then define a domain, which is where it will be active. So because you want to use VDB for everything, of course, you'll want to turn that domain into a VDB, and then you're able to do some operations quickly with it. For example, to call sources or call the simulator where it is within the bounds. So you want to do intersection operations. But if you look at this, you also need to do another operation, namely you need to create fluid outside of that bound so it can flow into the active region. And so you need to do offset operations. And this we realized was actually a serious bottleneck, because if your domain is moving over time and you have a very high resolution simulation, you are actually surfacing this airfield above you that might never actually show up in the dynamic simulation. You need to have the domain go up that high, because if a splash goes up there, you don't want to throw it away. But even though the solver will be sparse and not bother to simulate that high, you don't know that when you're building the domain ahead of time. So you end up having to surface this very high resolution box just for most of it to be ignored. Similarly, when you try and do the offset surface, we had to do more than the bandwidth. And so that basically you start doing dilation operations, and it gets hideously expensive to try and offset by 9 voxels this surface. So trying to find a better way to do these clipping operations, we started to think about a better way to define the fluid domain and still have the ability to do these sort of cylinders and camera frustum shapes. That led us to the idea that any convex domain can be represented by a bunch of half spaces intersected. So for example, this box can represent 6 half spaces, and the intersection of all of them can become my domain to clip by. What's nice, of course, with this is it's an implicit representation, so I don't have to actually, compute all the way to the top. I only have to deal with areas that I have to intersect with. But also, more importantly, it's very fast to offset. I can just move the half spaces along their normals, and then I can do an arbitrary offset. Now, this isn't quite a proper offset. For example, if I expand a cube properly, you'll get rounded corners. But if I expand a bunch of half planes, you'll stay with a sharp corner. But because we're looking very just a culling operation, this is more than necessary for our purposes. So now how to actually do this, it's open source days, so I figured I'll provide source code, and so I'm afraid that the following slides are all source code, but that's my justification, at least for these slides. So the idea is that the algorithm seems very simple. I'll just, VDB is a top-down structure, so I've got large nodes with smaller nodes inside of them, so I can just do a top-down recursion and throw away the node if it is outside, keep it if it is inside, and if it crosses the boundary, do something special with it. That sounds beautiful, and then you think, oh, I have to implement this. Oh gosh, it's going to be very complicated to deal with all the different templated classes I need, all the different edge conditions. But in particular, of course, it has to be multi-threaded, and then I have to think of how can I gather up all these nodes to multi-thread them on the right level at the right time. So this is where the dynamic node manager comes in, because it solves all the question of iterating over the grid for you. So this clipping operation, I should say, is similar to what the VDB clip tool already does. And if you try and mimic that, you find quickly you can't, because it was implemented on the tree nodes itself. And so unless you go to the VDB core library and update it, you can't write an equivalent algorithm. And one of the things we're trying to do in the TSC is do less stuff on those in the internal core library. So tools should be able to just use the tree nodes, but not have to actually add new functions to the tree nodes. Because whenever you do that, you have to recompile everything and affect anyone who is using your tools. And in Houdini, it's not really a choice, because we treat ourselves as a consumer of the core VDB. So dynamic node manager, as I said, allows you to solve these problems. So this is just how to set it up. It's still kind of scarier than I'd like. So the first line just declares an operation, which is a C++ class, which basically defines 3 operators for how to work on different node types. The second one creates a dynamic node manager out of the nodes in the grid. And the third one just executes it in a top-down fashion. So let's look at what that operation is, because this is the one where all the interesting code is. So you can see that it's templated on the tree type. I also templated on the operation. This is to go over subtraction, difference, or union. And then the constructor is just internalizing a bunch of data I'll use. So what I do for the half planes is I store an inner haul and an outer haul, because the only places that will have interesting values when you do an intersection operation is stuff within your plus or minus bandwidth of that surface. So if I'm outside of the outer haul or inside the inner haul, I know I'm in a constant region for the intersection operation. Then to actually implement it, you basically need to do 3 open parenthesis operators, which are basically called into depending on the type. The first type is the root node, and I just return true here, which says keep processing, please. Because what the dynamic node manager does is it will early exit if you return false and not process any of the children of that node, which is very important for this sort of operation. So after we get past the root, we're into the internal nodes. And the first thing I want to do is check for trivial acceptance rejection. So I can take the bounding box of my node, and I did everything in an index space here. So I can just check to see if this bounding box is entirely inside my inner haul, in which case, if I'm a difference operation, obviously I need to remove that. So I fill it with background. If I'm a union operation, I need to keep that. So I fill it with minus background, which means I'm inside the object. And in any case, I'm now done. I don't want to process these child nodes because I know they will be not affected any other way. The same rule goes for the being outside the outer box, but of course opposite sense for the different operations. Then we start getting to the interesting part. So this node in some way crosses over the active region of my convex hull. So I have to iterate over all children of this node. So it's kind of confusing in VDB because we often talk about a node maybe not having all of its children, but it's in a sense a node will have either a constant tile as a child or a pointer to another node as its child. So the difference there is whether or not this child pointer is set, but in either case there is sort of like a block of information there. So if there is no child, I want to do some early exits, because if I'm doing, for example, a union of a small convex hull inside a giant VDB, areas that are constant, I don't need to continue to recurse because there'll be no effect by unioning with it. So if I'm already inside, there's no change, so I can quit right away. And similarly, if I'm outside in other operations. Actually, this went 2 steps forward. How do I go backwards? Probably the small one. Nope. And I went 2 steps forward. Okay, let's get this. And well, I've hit it the wrong number of times. Oh, okay, it's like did it change order? Okay, no child. No, I'm missing a slide. Okay, so this went before the other slide, just different order. That's kind of surprised me. So the next thing we do is call the entire tile. And so this is the same operations we saw before, but in that child tile. So if that's entirely inside or out, we just replace it with a constant tile. And the important thing is when the dynamic node manager allows you to change your children before it recurses to them. So by erasing a child node, it will not be recursed to because it doesn't exist anymore. But the case where we fall through that continue loop and we don't have a child, in this case, we have a constant subtile, but that intersects our active regions. So something interesting is going to happen there, but it's currently constant, so it will not be recursed to. So we have to create a dense child there, which is what this does. So then we'll have something to recurse into. And at the end, we say, because we fell through, please continue and recurse from my children. So now, oh, sorry, I go forward. Oh, no, we're missing the, okay, sorry, that's a missing slide here. Okay, so there's a missing slide here, which shows the leaf iterator starting up, which again is, it's missing because it's boring. It's just, again, just colon if you're outside or inside. So let's immediately go to the interesting part, which is going over all the voxels inside, which is the 8 cubed, and you exactly compute your distance and do your union difference or intersection update. The one little catch here is that if you have a cube, this is fine. But if you have a cylinder and the artist decided they want a really beautiful cylinder with 1,000 sides to it, you might have 1,000 half planes here to process. So what we do first is we quickly go through the list of the half planes and find out which ones actually have their active area overlapping with this tile. And so you end up with only 2 or 3 that you actually have to process in the innermost loop, which is nice. It does do one extra check here because it should have been excluded if it has no active planes that overlap it, but you don't want to trust floating point math, so it's good to always double check. So that covers the what we did for convex clipping, and now we'll have a discussion of how to integrate with Mathematica.
All right, thank you. So my name is Greg Hurst. I'm a principal mathematician at United Therapeutics. And I guess before I get into the Mathematica, I guess I want to talk just briefly about my use case for VDB. So my company is a pharmaceutical company, and we're working towards 3D printing artificial organs, particularly the lung. And we use voxel-based 3D printing. And so VDB was a natural fit because some of our objects have up to 44 trillion voxels. So having a sparse representation has been a godsend. So with that said, about 1.5 years ago, I kind of needed to blend my workflow with VDB, and what I end up using is Mathematica. So I sort of work towards building this link. So the first question is, why am I using Mathematica? So I actually used to work there for about 5 years, so I kind of know the nuts and bolts of things, but basically OpenVDB kind of integrates very nicely with it. There's a slew of geometry built in. So for example, I can take an integral over a cow of sine of XYZ, get back a number, things like that. Or just work with a rich set of different types of regions and things like that. It has a really nice library for image processing, both 2D and 3D, tons of filters, tons of basically whatever you can think of. And then it has, all the NP complete graph theory algorithms you could ever want and more. So dealing with, capillary networks and things like that, we idealize them as graphs and have to do all these weird cuts and partitions and things like that. So Mathematica has been very good. So basically I wanted to be able to work in VDB to just have a seamless workflow. So currently, apologize, it's kind of hard to read there. I've been kind of one by one exposing the functions that are in VDB into Mathematica. It has been sort of driven by internal needs. So mainly dealing with narrowband level sets and fog volumes and things like that. So the plan is to have this released for version 10, as Ken was saying. Currently, there's about 68 exposed functions. Honestly, it could probably double by the time October rolls around, in addition to getting the CI ready and things like that, which is not exactly trivial. But let's actually take a look. So Mathematica is a notebook-based environment, sort of like a Jupyter notebook or something like that. So you basically hit Shift-Enter on your input, and then you get an output cell. And you can sort of work from there. So the first thing I want to look at are the available grid types you can access within Mathematica. And well, effectively, it's just every default grid that VDB ships with the addition of a byte grid, which is something that I've been using internally. And what's nice, the notebook interface is graphical. It's not just text-based. So if you just hit Shift-Enter and create a grid, it'll sort of output this in like a graphical form. It's still a computable object, but we got a little icon for each type. Sort of, if it's vector, you get a bunch of little vector plots and stuff like that. But basically, if you click the little plus button, you get a little more info about your grid. Next, we're going to take a look at an actual example. So within Mathematica, there's a function called example data where you can, in this case, I get a mesh region of a triceratops. And then on the next line, I specify my voxel size and my half width. And then I just ask to create a level set. So my NeuroVDB is OpenVDB level set of just my mesh region. And I get back this OpenVDB grid. And in this case, the little icon and the name indicate that I have a level set. Whereas in the past, if I can go back, if you just have a scalar grid and it's not marked as a fog volume or a level set, the icon will be different just to let you know that, hey, maybe something went wrong. I can ask for properties. So any of the properties that you might ask in VDB. In this case, I'm asking for all the properties. So it's a level set, it's tree float 543, the index bounding box, and so forth. But if I just want to say the index bounding box, I could have just passed in index bounding box instead. We can do, any type of modifications we want on the level sets. So in the first line, I'm taking my dyno and I am subtracting a cylinder from it. So cylinder is a built-in special region in Mathematica, and this OpenVDB link basically knows how to convert that into a VDB object, and then under the hood basically calls the CSG difference. And then after that, I'm going to do a little smoothing filter. So I'm going to do a mean filter with window 2. And the third argument, which is optional, I'm passing in 8, which means do 8 iterations of it. And then from there, we can actually take a look. So built into the notebook is a viewer, which is based off of the ray intersector class that basically comes in with VDB. And we can rotate, we can pan, we can zoom. I wrote a dinky little Cook Torrance shader just to make it look kind of nice. Or we can make the clipping closed and things like that. So yeah, I think right now we're looking at the plastic shading. So that's the rubber shading, and then if we open it up, we get all these metals and plastics and things like that. One important operation is going back to meshland. So basically any function that VDB has, all the optional arguments are also ported over. So on the left, we're just asking for the mesh of this smoothed object back. Typically, you want to set some adaptivity because your mesh can be quite huge. Here, I just go all the way up to adaptivity 1. The next thing I can do is, if I so choose to do, I can convert my level set into a fog volume. And now we get back a different little type of icon, this time saying it's a fog volume. But it is still a float tree. One nice thing about Mathematica, I was saying it has 3D images built in, so I can just ask the link to get back the 3D image of this. So this is the voxel representation. In Mathematica, image 3D is a dense voxel grid, unfortunately. There is a special option, which I don't have shown here, which basically says, hey, return me a downsampled version of a reasonable size. Typically, it's about 2 billion dense voxels. There's a bug in Mathematica where the front end will crash if you render more than 2 to the 31 voxels. So to make sure we stay below that. The other thing to note is that the default transfer function for 3D images in Mathematica is this yellow color. I'm not entirely sure why. Something else we can do, we can slice through our models. So if we just want to get back a 2D image, we can also zoom in and inspect. So oftentimes in my work, when I'm looking at capillary networks or things like that, I don't want to get back the full 3D object, especially because we're 3D printing. I just want to look at slices. Because our slices are so large, it is helpful to be able to zoom in and basically take a closer look at a certain area. And just to note, I just thought it'd be kind of fun to show that this also works on the Moana cloud. So we can sort of see inside the Moana cloud and basically see has a hollow shell inside. We can zoom in and look at the fog, and we can get a little bit closer. And note that I am importing this. So import and export also work. So if you want to import a grid, if your grid has multiple grids inside of it, you can specify a name to get the grid. And basically the same thing works with export. Something else, we can get the voxel and tile data back. So Mathematica has an efficient sparse array data structure. So if you want to get the voxel values, you can also get the positions along with it and store it as a sparse array to have them sort of coupled together. We can also get back the active tiles. And then here I'm doing a little bit extra to turn them into cuboids. so we can look at them in 3D as well. As kind of a fun example, so there's probably kind of an obscure function in VDB called OpenVDB fill with spheres. And actually, it's kind of an interesting distinction. So in Mathematica, a sphere is the two-dimensional boundary, and then the ball is the volume. So I've decided to call the Mathematica port OpenVDB fill with balls because we're filling it with the solid. So anyway, I'm just taking my dinosaur, filling it with as many balls as I can, upping the seed count to try to get as best picture I can. And then I'm extracting the radii, which is the second argument to ball. And I'm basically taking the log of the radii and rescaling it and then mapping rainbow color over it. And we get this kind of interesting picture. Some nice notes about notebook interfacing or like workflow. Mathematica's interrupter can communicate with OpenVDB. So any OpenVDB routine that can be interrupted, you can interrupt it from your notebook setting by just doing Command period if you're on a Mac, and I think Alt period if you're on Windows. If OpenVDB throws exceptions, Mathematica will catch it. The link also tries to do a good job of preventing VDB from throwing exceptions. That was almost like an exception. So there will be top level code if, let's say, you pass a vector field grid into OpenVDB filter, it'll check beforehand so the C code isn't even called to throw the exception that, hey, OpenVDB filter can't even deal with a vector grid. There is autocomplete in the notebook. So in this example, if you're wanting to do a filter, there's really only 5 choices. You get this nice pull down menu and you don't have to type Laplacian if you don't want to. And then there's highlighting to indicate if you are missing any arguments, have any extra arguments, or some things are invalid. So OpenVDB transform, that's the function that can basically apply any affine transform to a VDB. So rotate, scale, shear, translate, things like that. So obviously you will need a second argument. So if you just pass in the VDB itself, it can't do anything. So we get a little red caret saying, hey, you probably want a second argument. Or in the second example, I am passing in a scaling transform, scaling it anisotropically, in fact, but I am passing it something called wrong option, arrow 1. Well, that's a wrong option, so it's red. And then in the filter, there are only up to 3 arguments. Note that the third argument is optional. The third argument is the number of iterations to apply the filter. The default setting is just 1. So if you go past that, it'll basically turn red and say, you probably don't want that. So currently, it is up to you to build the binary. So there is a file called buildsettings.m where basically you need to go in there and add any extra build settings before compilation. Because there is an extra kernel that is compiled that actually communicates with the dynamic library that OpenVDB gets compiled to. So you add any options. You can specify your compiler of choice. I use Clang. I'm on Mac. And then within your Mathematica notebook itself, there's a function. It's sort of hidden in a developer context, but it's OpenVDB link backtick developer backtick recompile. This should be a one and done call. So this is sort of compiling it on your machine itself. And then if all goes well, you'll never have to do it again unless there's an update or something like that. Currently, it takes about 5 to 6 minutes to compile, at least on my machine. And for anyone that's interested in actually contributing, we have a slew of unit tests. Currently, there are almost 1,400 unit tests, and this basically leverages Mathematica's built-in unit test framework. So I sort of have a hierarchy of unit tests, so CSG unit tests, distance measure unit tests, filter unit tests, etc. And if there are anything wrong, Mathematica has the built-in functionality to sort of drill down and find the test that went wrong, and you can sort of address from there. So if you're ever interested in developing, we'll be able to have unit tests to make sure things go smoothly in the future. Yeah, and sort of under the hood, kind of mirroring Jeff actually, a lot of this is just glue code. And for example, if you want to get back that dense image 3D object of the Triceratops, well, down there where the red arrow is, I'm just using the dynamic node manager. And really, I think I just need to use node manager here. And effectively what's happening is, as I iterate over my grid, I'm only showing the internal node function, but if a bunch of criterion are met, one of the criterion, and one of the things I didn't talk about, is the image 3D function. You can give a bounding box and say, I only want the dense image over in this region. So part of what the dynamic node manager class here, or the class fed to the dynamic node manager, is doing is making sure that this node overlaps with that bounding box. And then if so, literally, let's just do a triple for loop and then populate the dense image with that constant value of that tile. And then something similar for the leaf nodes as well. And yeah, I'm really excited about this project. It has really streamlined my workflow, really sped things up. And the idea is to have it for 10. There is an active pull request up right now. Part of the challenge will be to integrate it with I guess with VDB's built-in testing framework itself. So that way, when VDB itself updates, we can make sure that the Mathematica link also doesn't break. So it's kind of a two-way street there. So definitely feel free to check that out. And thank you. Yeah, and if you have any questions, feel free to email me or come talk to me after this. Yeah. Thank you.
And I think we're towards the end there. Does anybody have any questions? I can check on the computer here. If anyone has any questions, you can raise your hand real quick. I will run the mic over to you. And I don't see anything on the chat either. So, oh, we got one question. So sorry. I missed it.
No, it's about the NeuralVDB. I was wondering how fast it decompresses actually back, so we can access that.
That's a good question. So we have two.
Do you mind if I give you the microphone just so the people in the Zoom?
It's a great question. So we have two modes, or two sort of applications for NeuralVDB. The one that we are pushing for most at this point is as a file compressor. For that one, we are trading perform or decompression time for a reduced footprint. And so I think the Disney Cloud is on the order of 20 seconds to decompress. Some of the smaller models obviously much faster. Then we have another configuration. So actually, I should have mentioned that NeuralVDB itself is still using a tree sort of layout. It's still a hierarchical neural network. And so what we do is we have one version where we have neural representations at 2 levels. That's the one that goes for maximum compression. And then we have another one where we only apply it to the leaf nodes. And that's for real-time applications. For that one, it's very fast, but obviously the compression ratio is smaller. But we have, there's a paper coming out tonight that has lots of tables with actual performance numbers and stuff, if you're interested.
Cool, thank you. We have time for maybe one more question, if anybody else has any. All right, well, we have about a 10-15 minute break. There's some snacks and food out there. There's a lovely popcorn bar and I believe jelly beans and assorted things. So help yourself, chat amongst others. Some of the project folks will be here and they'd love to talk with you, and we'll be back right afterwards. And I think Moonray is right after the break. So we'll see everyone then.